Contrary to their complex output, diffusion models are trained on a surprisingly simple objective: predicting noise in a corrupted image. This stable training process is what allows them to overcome the notorious mode collapse and instability that plague generative adversarial networks, or GANs. Ultimately, their ability to reliably produce diverse and high-fidelity results with precise user control cemented their dominance over the faster but less dependable GAN architecture. The generative AI landscape is dominated by a few key players, including corporate giants like OpenAI with its DALL-E 3, Google with Imagen, and the independent Midjourney Incorporated. A pivotal role is also played by Stability AI, the company behind the prominent open-source Stable Diffusion model. Crucially, the nonprofit German organization LAION provides the foundational open-source datasets that power much of this ecosystem's development. The primary trade-off between open-source models like Stable Diffusion and proprietary systems like Midjourney revolves around flexibility versus curated quality. Open models offer unparalleled adaptability and transparency, allowing for fine-tuning and community-driven innovation at the cost of a steeper learning curve. Conversely, closed ecosystems provide a highly polished, user-friendly experience with consistently aesthetic results, but limit user control and customization. The LAION 5B dataset, a massive, publicly accessible collection of 5.8 billion image text pairs, became the bedrock of the open-source movement by democratizing access to web-scale training data. This non-commercial resource, created by a German nonprofit, enabled entities like Stability AI to train powerful foundation models without the immense cost and legal hurdles of curating a proprietary dataset of similar magnitude. Its existence directly fostered a competitive and innovative open-source ecosystem that could rival closed, corporate-led development. Early generative models often suffered from a mean averaging problem, producing blurry, indistinct images by averaging all possibilities from the training data. Diffusion models ingeniously solve this by reframing the task from direct generation to iterative reconstruction. Instead of a single predictive leap, they learn to reverse a gradual forward process of adding noise, ensuring that each step maintains coherence and avoids collapsing into a generic, averaged-out result. In the forward diffusion process, the scheduler acts as a deterministic controller, dictating the precise amount of Gaussian noise added to an image at each discrete time step. This is not a random degradation, but a carefully calibrated process following a predefined noise schedule, often a variant schedule like a linear or cosine schedule. The scheduler ensures that by the final time step, the image is transformed into pure, unstructured noise, providing a predictable trajectory for the model to learn to reverse. During the reverse process, the UNet model is not trained to predict the clean image directly, but rather to predict the specific noise component that was added to the image at a given time step t. The model receives the noisy image x_t and the time step t as input, and its weights are optimized via backpropagation to minimize the mean squared error between its noise prediction and the actual noise used in the forward process. This focused objective of noise prediction proves to be a more stable and effective learning target than predicting the denoised image itself. While autoregressive models generate images sequentially, one pixel at a time, this process is computationally glacial for high-resolution images and struggles to maintain long-range spatial coherence. Diffusion models are qualitatively superior because their iterative denoising operates on the entire image representation in every step, allowing the model to refine both global composition and local details simultaneously. This holistic, parallel approach is vastly more efficient and effective at producing coherent, high-fidelity images compared to the cumbersome, one-dimensional path of pixel-by-pixel generation. Operating directly in the high-dimensional pixel space made early diffusion models prohibitively slow and memory-intensive. The key innovation of latent diffusion models was to perform the computationally expensive diffusion process not on the image itself, but within a much smaller, compressed latent space. This strategic shift, enabled by a powerful autoencoder, dramatically reduces the computational load, making high-resolution image generation feasible on consumer-grade hardware. The Variational Autoencoder, or VAE, performs two critical functions in the latent diffusion architecture. First, its encoder acts as a powerful data compressor, transforming a high-resolution image into a compact but information-rich latent representation where the diffusion process occurs. Second, after the UNet completes its iterative denoising in the latent space, the V's decoder serves as the final stage reconstructor, translating the clean latent vector back into a detailed, full-resolution pixel image. Unlike a standard autoencoder that maps an image to a single, deterministic point, a variational autoencoder maps it to a probability distribution within the latent space. This variational approach ensures the latent space is smooth and continuous, preventing gaps and making it more robust for generation. This probabilistic encoding allows the model to generate subtle variations of the same concept and provides a more structured canvas for the diffusion process to operate on. The clip text encoder is the crucial bridge between human language and the model's generative process. It takes a raw textual prompt and transforms it into a high-dimensional numerical vector, known as a text embedding. This embedding is not just a keyword lookup, but a rich representation of the prompt's semantic meaning, existing within a shared semantic vector space, where it can be directly compared to image representations, thus providing an interpretable instruction for the UNet. Traditional image captioning models learn a narrow task, generating a single descriptive text for an image. Clip's contrastive learning approach is far more powerful because it learns from a different objective to identify the correct text-image pairing from a massive batch of negative examples. This forces the model to learn the underlying semantic essence that connects a concept across modalities, resulting in a more robust and generalizable understanding of text-image relationships. The UNet is named for its characteristic U-shaped architecture, which is perfectly suited for the denoising task. It consists of a contracting path or encoder that progressively downsamples the input to capture hierarchical features and context, and a symmetric expanding path or decoder that upsamples this information to reconstruct the output. The key to its effectiveness is the use of skip connections that feed high-resolution feature maps from the encoder directly to the decoder, preserving fine-grained details. As the UNet's encoder path compresses the input, it captures low-frequency contextual information but inevitably loses high-frequency details like precise edges and textures. Skip connections solve this by creating direct data pathways from the encoder layers to their corresponding decoder layers. This hierarchical feature fusion allows the decoder to combine the abstract, semantic information from the deeper layers with the precise spatial details from the skip connections, ensuring the final output is both contextually correct and sharply detailed. The architecture employs a clever two-stage compression strategy with distinct goals. First, the VAE performs a compression for computational efficiency, moving the entire operation from the massive pixel space into a manageable latent space. Within this latent space, the UNet's encoder path then performs a second, hierarchical compression for semantic understanding, progressively abstracting the latent image to analyze its contents at multiple scales. Classifier-Free Guidance, or CFG, is a clever technique that provides strong directorial control by running two parallel predictions within the UNet at each step. The model generates one prediction that is conditioned on the text prompt and another unconditioned prediction that ignores it. By calculating the difference between these two outputs, the model isolates the semantic direction of the prompt and can amplify it to steer the generation process with high fidelity. The CFG mechanism calculates the final noise prediction using a simple but powerful formula. Final underscore prediction equals unconditioned underscore prediction plus guidance underscore scale asterisk, condition underscore prediction, unconditioned underscore prediction. This equation first finds the directional vector pointing from the unconditioned to the conditioned prediction, which represents the pure influence of the prompt. This vector is then scaled by a guidance value, typically around 7.5, and added back to the unconditioned base, strongly pushing the result towards the desired concept. The CFG process can be intuitively understood as a form of vector arithmetic for steering creativity. The subtraction of the unconditioned from the conditioned prediction effectively isolates a pure prompt direction vector, representing the semantic essence of a user's instruction. By amplifying this vector with the CFG scale, the model is commanded not just to head in that direction, but to do so with strong conviction, preventing the final image from being a weak compromise between a generic image and the prompted one. The training and inference phases are fundamentally different in purpose and execution. Training is a one-off, computationally massive process where the model learns to predict noise from a vast data set of images and text, with the objective of minimizing prediction error. In contrast, inference is the fast, practical application where the trained model takes a user's prompt and a random noise seed as input, running an iterative denoising loop to generate a new image. Training the model by iterating through the full forward noising process for every sample would be computationally infeasible. The efficient training strategy instead selects a single, random time step t for each training example and adds the corresponding amount of noise in one go. By exposing the UNet to millions of examples at randomly chosen noise levels, it effectively learns to denoise from any point in the trajectory without the need for the full, slow, iterative process during training. The inference loop is a collaborative dance between the UNet and the scheduler to achieve progressive refinement. In each step, the UNet predicts the total noise present in the current latent image, and then the scheduler uses this prediction to mathematically calculate the state of the image at the immediately preceding time step, t1. This process, which subtracts a carefully determined fraction of the predicted noise, is repeated for a set number of steps, each time moving the latent from a state of pure noise closer to a clean representation. The core diffusion architecture is adapted for tasks like image-to-image by altering the starting point of the reverse process. Instead of beginning with pure random noise, the process starts with an existing image that has been encoded and partially noised by the forward process. The UNet then denoises this latent, guided by both the information from the original image and a new text prompt, allowing for stylistic transformations or edits. The logic for in-painting cleverly uses a mask to constrain the diffusion process. After each denoising step performed by the UNet, the system replaces the pixels in the unmasked region of the generated latent with the corresponding pixels from the original noise source image. This masked region logic forces the model to concentrate its generative power exclusively within the masked area, while ensuring the final result blends with the surrounding, untouched context for seamless coherence.